Okay, the next topic we're going to take up is it's section 5.8 in our textbook, and it is called series motors. And the series motor is identical in construction to the earlier versions of DC motors that we looked at, primarily the shunt or parallel field connected motor. The only difference is how we connect it. Okay, and so what we're going to do is we're going to take this same motor, and instead of having a parallel field, we're going to have a series field where all of the armature current runs through the field. Okay, again, this field is the way that we produce the magnetic flux that we need to get this energy transfer to occur. Now, even though that's the only difference in the construction of this series motor, the characteristics are going to look completely different than what we saw with the parallel setup. So let's look first at a schematic of this. And again, it's going to be very simple, as all of these motor circuits tend to be. And let's look at that and get an idea here of what's going on. Okay, so here's what we have. We have a series motor connection diagram here in figure 510. And what I want you to notice is that here's the source voltage, and here's the designated positive terminal. And what's happening here is that this field, this would be, the source of our magnetic flux. It is connected in series with the armature, okay? So all of the current that flows through the armature flows through the field. Now, think about that for a second. And if the load increases, the current's going to increase. If the current increases, then the field is going to increase. And we already know from our equations that we have, the increased field will provide more voltage available, right? And so, you know, it's sort of this feedback situation where the motor is going to respond to the load that's connected to it. This field, actual conductor, it is a thicker, larger gauge wire so that it can carry more current through it. And so, you know, that's one thing that makes it different. And again, the biggest thing that we look at with this is that, you know, the series motor flux per pole depends upon the armature current, which depends upon the load, okay? So when a series motor operates at full load, the flux per pole is the same as that of a shunt motor that has the identical speed and power. However, where the big difference is at motor startup. And at startup, we know that the armature current is always higher, much higher, right? And so what we see is that the flux per pole is going to be greater. And because the flux per pole is greater, the motor torque is going to be greater. Now we'll look at some examples of DC series motor and the effect of all this torque. And we see these amazing vehicles, electric vehicles that have this, you know, 0 to 60 in less than 2 seconds kind of stuff. I mean, it's just, you know, the torque is immediate and high and applied directly to the wheels. And I'll show you some stuff later where we compare, you know, an electric car to internal combustion engine. And you can just see the electric vehicle is blowing these cars off, you know, on the short. Now, eventually, over time, the way that the construction is that, the electric vehicle loses some of its advantage beyond startup. But anyway, we'll get into that further on down the road. Let's see. He says that it might be good for us to look at and contrast the differences between the torque speed curve for the parallel connected or shunt connected motor, which is in figure 5.8. And, we kind of remember that, right, from earlier. And then to contrast that with the series connected motor here, okay? And so if we look at that, we see a whole different set of curves, where on the bottom again we have one curve which is going to be torque versus speed, and another is torque versus current. Now, the torque versus current in the shunt, it was more of the straight line, the y equals mx plus b kind of curve, but still the series, it's close to that, right, in its construction. But what is largely different is the torque curve that we're looking at. If you'll remember the torque versus speed curve on the shunt connected motor, it was almost vertical. What did it? It was kind of like that. And for this curve, look at what we're looking at here. Big difference between those curves. And so what we're seeing is what we were just talking about, is this very large starting torque, the starting torque. Now the torque, goes down, and the modeling of that is not so simple because the curve is not straight, but still, we can see the trend across there. But what we're looking at is the starting torque here. Okay, so let's talk about that just for a second. Now, one other thing that's mentioned, we have the large starting torque, but our textbook tells us if the motor is operating at less than full load, the armature current and the flux per pole are smaller than normal. Now let me pause right for a second and put this equation back up here. So we can see from this equation that if this series motor is running at less than full load, then the armature current is going to fall. And if the armature current falls, since this is series connected, this flux per pole value is going to get smaller. Okay? Now, again, inverse relationship, right? So this flux per pole gets smaller, the speed is going to increase. Now, so he tells us this weaker field causes the speed to rise in the same way that we saw the speed rise with a shunt motor with a loss of the field. Okay, so for example, he says if the load current of a series motor drops to half its normal speed, the flux diminishes by half and the speed will double. If the load is very small, the speed may rise to very dangerous high levels. Okay, so with the shunt, we had to guard against loss of field. Okay, we couldn't have that because the loss of the field would cause this speed to get in what we call a runaway condition. And with the series, we cannot have a situation where we don't have a load connected to it. Excuse me, and without the load, the speed reaches very high levels. And, you get into particular problems with centrifugal forces, tearing the windings out, the armature becomes destroyed, and eventually the motor would be. So, okay, so series must have load, and shunt must have field. Okay, so we got to remember those two. All right, let me stop this one. This is section 5.8.